All right. Hello, everyone. This is the lecture number 12 of our course on Introduction to Quantum Computers, and today we're gonna start our discussion about the essentials of quantum computing hardware, and we're gonna start with the photonics for quantum computing. So it will be about the optics and photonics and how it can be used to develop quantum computers. But let us briefly recap what we've done last week. So last week we finalized our discussions about the basics of quantum algorithms. So 2 weeks ago we discussed the Grover search algorithm, and last week we dedicated our time to Deutsch's algorithm that allows to, for example, to solve this Deutsch's problem on defining the type of a oracle function, either constant or balanced. So the classical approach requires two calls. The quantum, in this very simple scenario, it requires just one call. And so we discuss how this algorithm works in somewhat details, and just as a remind you, it is equivalent to the optical scattering experiment, like this one. So for example, if you have a coin, and you want to detect either this coil gets two identical sides or different sides, you can send a wave and make this wave scatter from both sides, and then overlap the scattered waves, so they interfere. And if the interfere pattern is somewhat symmetrical, then the coin is fake, right? It gets two identical sides. Otherwise, it's a fair, good coin. And so this is kind of an example of how the wave phenomena can help us to solve some kind of these problems. So then we discussed the generalization of the Dodge algorithm, and this one is called Dodge-Joyce algorithm, and this one for the multi-dimension function f and multiple qubit system. So we discussed how this problem scales classically and in a quantum realm, and discuss the speed up of this algorithm comparing to the classical one. Next, we discussed the purpose of the Shor's algorithm. Unfortunately, we don't have time to dive into details of this one, but today this Shor's algorithm is considered one of the most important algorithms. It's very tightly connected to the problem of Fourier transform of functions and quantum Fourier transform in particular, and it's related to finding the patterns in the sequences of numbers. Okay, and we discussed that this quantum computing approach, wouldn't help to make the Fourier transform in a faster way. However, it would allow us to find the factors of factor numbers of some large numbers, right? So this can be used, for example, for security purposes. All right, so then we also said a few words about the quantum Fourier transform. Quantum Fourier transform, that is basically the change of the basis from computational to the Fourier transform and vice versa. And yeah, quantum random circuit, which is very simple algorithm for understanding. This is just a quantum circuit, a system, a register of n qubits, and then you apply the unit operators and the measurement operators, measurement gates randomly in time. So you change the wave function, then you make the wave function collapse, then you change it collapse in different qubits, and the result of all this is the sort of the random walk, right? Random walk realization, but for the quantum realm. So this algorithm or this type of circuit, quantum circuits, is known as like a benchmarking circuit. For example, this one has been used for benchmarking the quantum circuits, quantum computers, and for example, the famous work on quantum supremacy made by Google a few years ago has been done for this particular algorithm. And there is, of course, a large body of works dedicated to simulation of quantum systems using quantum computers, and this is maybe my favorite part of this research, because it will allow us to calculate the spectra of large molecules. It will allow us to maybe design molecules, including some maybe medicine, maybe some materials for different purposes. So it's very actively developing research area today, and and I would say in general the development of quantum algorithms is much well it develops much faster than the development of the hardware of quantum computers, because of many challenges in the area of hardware. So we definitely have to say a few words and dedicate maybe two left classes for the quantum hardware. And today we're gonna start with the photonics and photonic elements for the quantum computing. So have all this said, I wanna share my screen. Okay, so I prepared this presentation because I believe that it's much more instructive to discuss this photonic part about photonic hardware for the quantum computing, using these illustrative slides rather than writing down the formulas, etc. So yeah, so here's the chapter or subchapter 5.1, photonics for quantum computing. All right, and so a few words about photonics. So photonics is the area of science that discusses the effects of light and how light affects or interacts with matter. Okay, and the very well known light source is the laser. As you of course know, laser is very popular. The light source today can be found in many applications, and of course in research lab. So if you visit our research lab here at FIU, you will find many lasers on the optical tables. And the purpose of this system, the laser, is to generate a light of one particular color or one particular wave number or wavelengths. Okay, so yeah, so different wavelengths corresponds to different color, and one can, so basically light is a wave, right? It's thought to be a wave for many years, but in the last century it has been discovered that light consists of elementary particles, photons, and in fact the light beam, like shown here, it consists of many particles or photons that have the wave phenomena, okay, or manifest some wave phenomena, as we will discuss today. So having the photon detectors or even single photon detectors, we today able to detect a single photon. Okay, so a typical photon detector shown here, and here is the result of photon detection. So the x is the time in nanosecond, and y-axis is the voltage, and each spike on this figure corresponds to the event of detection of a single photon. Okay, so we can dim the light beam by absorbing it or using some sort of a light absorber, light dimmer, and this way what we do is basically we reduce the number of these spikes per unit of time. Okay, but due to this absorption of light, okay, the amplitude of each spike doesn't change. So it indicates that the light consists of the photons, and the photons are absorbed as a whole. And yeah, so using the absorber, we cannot absorb a half of a photon. Okay, so it must be considered as a one particle that is destroyed when it's absorbed, okay, or detected using the photon detector. Okay, so light is made of photons, and the photons are the fundamental particles of light, and they possess unique characteristics that make them ideal candidates for the quantum computing and quantum information science and research. One particular peculiarity of a photon is their speed, right? They propagate at the speed of light, which is the largest velocity in nature, and presumably the photonic system supposed to work at a very high speed. Another characteristic that characterizes the photon is that the photons don't interact. So you can take two laser beams, like laser pointers, and then you can cross the light beams and you will see no mutual scattering. So The photons don't interact. They don't scatter on each other. And this has pros and cons in terms of application of photonics, application of photons. And maybe another characteristic is that the quantum state of light, as we will discuss, can be preserved for a very long time. Okay, so for example, if we encode the quantum information in the state of the polarization of a photon, this state of polarization of a photon can last for minutes, hours, or even maybe days. So without interaction, for example, in cosmos, right, in space, if light doesn't interact with matter, then the state of a photon will stay unchanged for a very long time. In drastic constant to other types of quantum information units, to other qubits. So how we encode the information into a state of a photon? So there are several approaches, and I would say the two most important are propagation direction encoding, when we have like photon propagating one direction, like up and down, and left, right. Okay, so these two directions, vertical, horizontal, we can encode the quantum information in this propagation in propagation direction. Another approach is to encode the information into the polarization state of a photon. And first, we start our discussion with the propagation direction encoding. Okay, and the first point here to notice is the behavior of a single photon with a piece of glass, like with a window. Okay, so you know that if you have light, it propagates through the window. The most of the light passes through the window, so the window is transparent, but of course the part of the light bounces off from the surface of the of the window, and we get some reflection, right? So we can see, for example, ourselves, some objects in reflection. However, it's very interesting to think about this process in terms of one single photon. Okay, so the same holds for one single photon, and when one single photon comes to the window, it also bounces. It also somehow decides either to propagate through or bounce off or reflect from the glass. Okay, and according to the quantum mechanics, as we discussed, before we measure the photon being reflected or transmitted through the surface of the window, we have to consider the both amplitudes simultaneously. Okay, so even at the level of one single photon, here is this quantum randomness for the photon to propagate through or reflect from the glass, from the window. And before we measure it, we cannot say if the photon passed through or reflected from the window. We have to consider the two possibilities at the same time. Okay, in terms of vectors or states in the vector representation, we might say that in the input we have the normalized vector 1, 0, 1, or the first element corresponds to the horizontal propagation, and second element of this vector corresponds to the vertical, or better say, the first element in this picture corresponds to the propagation from left to right, and the second one, it corresponds to propagation from right to left. So we have the normalized vector in the input, amplitude is 1, and then for the transmittance, for the transmitted wave, we've got this a part of light transmits from the window, and it's described by this T, which stands for the transmission coefficient, which is a complex valued, can be function, for example, function of frequency of light or wavelengths. And part of it reflects, which is described by this R small, which stands for the reflectance, reflection coefficient. Okay, and the resulting state of a photon after the act of interaction with the window gets the state TR, so part, or like there is a finite probability to pass through, there's finite probability, or better say amplitude of the probability R small to be reflected from the surface. Okay, if we now make this glass slab to be balanced, which means exactly half, exactly 50% of the light passes through, 50% of the light reflects from the surface of this light, of this glass. In this case, this piece of glass is known as beam splitter. Okay, so it splits the beam of light, so that, for example, in the input we have this vector 1, 0, and in the output we have 1 over square root of 2, 0, and the second one is 0 and 1 over square root of 2 in reflection. So that the total state of the photon, of one single photon, after interaction with this beam splitter, gets this vector 1 over square root of 2 and vector 1, 1. Okay, so this is exactly perfectly superimposed state, the state in the balanced superposition. And we know, and we see that in this case, this element, this beam splitter, works as a Hadamard gate. All right. So the purpose of the Hadamard gate is to take the state 0, as in this case, and create the perfect superposition state 1, 1. Right. So equivalently, this beam splitter, in terms of in the matrix representation, can be represented in this Hadamard matrix form. And so this is how it looks like in reality. So basically it's just a piece of glass with some coating on the surface that allows it to reflect just 50% of the light. So another optical element that also can be used as a quantum gate is a mirror. So, for example, mirror. The light. So mirror is an optical element with the 100% reflection coefficient and zero transmittance, right? So in other words, in terms of vectors, the mirror converts the 1,0 state into 0,1 state, or a photon that propagates from left to right to the opposite direction, a photon in the opposite direction. And in other words, this element, the mirror, works as a bit flip gate or X gate. If we encode the quantum information in the propagation direction. And another example of a quantum gate is a phase shifter. Okay, so essentially, phase shifter is a thicker piece of glass. Okay, so when light propagates through this glass slab, it acquires some extra phase phi. Okay, so for example, if I have again the state 1,0 in the input, the light reflects from the surface and it gets state 0R because of the reflection. But some part of this light passes through, and due to this going through the glass slab, it not only acquires this transmission coefficient, but also changes the phase of the wave that goes out from the glass. Okay, so this element adds some additional local phase to the amplitude of the transmitted wave. And in other words, this element works as a P gate. All right. Working with left-right propagating beams not feasible, and it is much more useful to, or much more feasible to work in the horizontal vertical domain, right? So for example, if I consider a beam splitter like this, it could be a cube composed of two prisms, right? And light can scatter or reflect to the vertical direction and or go through, or in other words, in the horizontal direction. And in any ways, so after passing through the beam splitter, we get vertical photon and horizontal photon. And of course, these two photons are, or these two states that corresponds to these two photons are orthogonal, because a single photon it goes to either to the horizontal state or to the vertical state, but not in the mixture of the two. Okay, so these two states are orthogonal, and this is denoted by this Dirac notation, inner product of two states. And of course, we normalize the states, so the inner product of the same state is 1. Again, if this beam splitter splits perfectly 50-50% of the photons in the vertical horizontal directions, this beam splitter works as a Hadamard gate. And for example, if my state is horizontal, so it propagates horizontally, the beam splitter creates vertical and horizontal with the same probability amplitude, if you're talking about one single photon. Okay, there is another opportunity here. If I send the wave in the vertical direction, it again creates vertical and horizontal with the same probability amplitude if the beam splitter is balanced. However, in this case, I must put this minus here before the second amplitude, which gets two reasons, physical and mathematical. Mathematical reason is that this beam splitter as a Hadamard gate must be unitary operator, right? And but the physical explanation here is that these two prisms, they get the coating, and when light reflects from the coating, it changes the phase to the by pi, okay, 180 degrees, and it causes this minus to before the second amplitude. All right, so what I can do with these beam splitters? So I know that beam splitter splits the state of one photon into the two amplitudes. So for example, if I have the horizontal incoming photon, it's split it into two amplitudes with the same probability amplitude, horizontal and vertical states, okay? And then, for example, I can apply this P gate, which changes the phase of, for example, the horizontal amplitude of the photon, okay? And then after reflecting from another mirror, I can combine the both amplitudes again using the second beam splitter. Okay. So this element, as if you look closely at this optical setup, right? We notice the first beam splitter that works as the Hadamard gate. Then we have another gate which changes the phase of one of the states of the qubit, which is P gate. And then we have another Hadamard gate as a beam splitter that closes the interference. So we discussed this system in the section about the interference, right? Or we call this the golden single qubit circuit. Okay, so in this case, this is the optical realization of that system, of golden single qubit gate. All right, so we calculated the probabilities in that part and found that the probability, for example, of probability of finding the of the vertical photon and the horizontal photon, these probabilities depend on the on this phase phi of this P gate. Okay, so if I change this phi, the probability amplitude changes from 0 to 1 and then to 0 again. It's important that because of this change of the phase, in result, if you measure the light, for example, in this vertical direction, the result of this measurement is so-called the Mach-Zehnder interference rings, interferometer rings. Okay, so these bright and dark states correspond to the states of high probability of finding photon and low probability of finding the photon. Okay, and it's very it's very important that this interference pattern is very sensitive to the value of this phase. Okay, at the same time, the value of this phase is defined by the product of the wave number and for example, the distance that light travels through this P gate, which again can be just a piece of dielectric. Okay, and at the same time, the wave number is inversely proportional to the wavelength of the light, lambda here, and in the visible range, the wavelength varies from 400 up to roughly 700 nanometers. So in any case, this is the matter of hundreds of nanometers. Okay, and using this interferometer, we can detect the changes in phase or the changes in the phase with tens of nanometers or even nanometer with nanometer resolution. All right, so this is called Mach-Zehnder interferometer, and this is one of the most sensitive systems highly used for sensing applications. At the same time, now I can consider measurement. So now I want to measure a photon either in the upper or lower channel, here or here. So for example, I measure it in the lower channel. So measurement of a photon means that we capture the photon and destroy it, for example, through absorption of the photon by some material here. Or I can put just the detector there and detect the photon. And if my system gets two channels, every single photon must be considered to travel along the both channels, the both opportunities here, because the beam splitter splits the amplitudes right into two states. However, if I measure the presence of a photon, for example, in the lower channel, okay, I know that if the photon passed through the circuit, through the system, it definitely passed through the upper channel, because otherwise it would be absorbed in the lower channel here. In this case, as you can notice, we completely destroy the interference. So now the outcome of this setup, for example, probability of finding the horizontal photon, is given by just 25%, 0.25, because the beam splitter splits the light beam into two beams with 50% probability, or in terms of one photon, it splits the probability amplitudes in half, right? And if 50% of the photons, or 50% of the time a single photon is absorbed by the detector over here, the other 50% go through the system and then again splits by the second beam splitter into two possibilities, and each gives 25% of the probability. So say I send 100 photons in this horizontal state, and I can find or can detect 25 photons in the upper state in the output, or 25 photons in the horizontal state. In average, of course. In reality, these numbers could fluctuate, but if I increase the number of the input photons up to millions, I would get exactly 25% in the output. And the same holds for the upper channel. If I put my detector in the upper channel and measure it, again, this act of measurement breaks down the interference, so no interference here anymore. And again, I get 25% of probability of finding a photon either in the vertical or horizontal direction. So in this case, the photon behaves as a particle. Okay, so as a particle, it comes to the system, bounces off from the beam splitter, then reflects from the mirror, and reflects, absorbs, but another photon bounces off again from the beam splitter, propagates to the mirror, bounces off here, and then bounces off from the second beam splitter, and it gives the 25% of probability. So it's exactly as would is exactly the behavior of a classical particle behavior. However, if you remove the sensor, if you remove the detector, the photon behaves as a wave. Okay, so single photon travels either in the upper channel or in the lower channel, and we don't know in which of them. And on top of that, we must consider the photon as it travels through both channels simultaneously, even single photon. This effect leads to the fact that, for example, if I remove this phase gate and make the channels balanced, okay, I can get 100% in one of the channels. For example, 100% of probability of finding the photon in the upper channel and 0% of probability finding the photon in the horizontal direction. Okay, so this is the result of single photon interference. So the interference, or better say the probability amplitudes of a single photon, interact with themselves, and result of the interference, for example, give the 100% of probability of finding a photon in the vertical direction. Of course, changing the distance between the beam splitters can make the horizontal photon 100% probability and vertical 0. Or changing the orientation of the beam splitter, so it flips the signs in the probability amplitudes. All right. Again, so in this balanced case of no phase shifter, we can get 100% of probability in the vertical direction and 0 probability in the horizontal, which means the photon does not appear in the horizontal direction whatsoever. But if I put a absorber in either of these two channels, it immediately causes 25% of the photons go to the horizontal direction. Okay, so I absorb photons in one of the channels, and this absorption causes increase of the number of the photons in this horizontal horizontal direction. So it's the matter of the photons being seen or not. Either way, like if I detect the photon, it behaves as a classical particle. If I don't detect the photon, it behaves as a wave, and it can interfere with itself. Can interfere, or actually interferes with itself. So as a consequence of this single particle interference, there is a famous Elitzur-Weidmann bomb fold experiment. Okay, so let us consider some specific bomb that can explode, okay, or not, whether depending on whether the bomb is defective or operational. So the bomb is assumed to get a detector shown here by this star. Okay, and if the detector is functional, or the bomb is functional, then this detector absorbs the photon with perfectly absorbs the photon with 100% efficiency. However, if the bomb is defective and detector is defective, it allows to the photon go through the bomb, like through this channel, without interaction with the detector. And so in some sense, this is realization either this scenario when the bomb is defective, right? So the photon passes through without interaction, and we get, for example, 0 photons in the horizontal channel. Or when the bomb is operational, is functional, then we probe the one of the channels, and it leads to the appearance of 20% of the photons in the horizontal direction. Okay, but we don't know either a particular bomb is operational or not, and the question that Elitzur-Weidmann asked is, can we certify the bomb without exploiting it? So we test the bomb, and classically, if we test a bomb, it would exploit or not. If it exploited, then the bomb was functional. If it doesn't, then it's defective, but useless, right? But can we use quantum to certify the bomb without exploiting it? And the answer is yes, and this is basically the consequence of our previous discussion. So if the bomb is defective, the photon goes through it without interaction, and the probability of finding the photon in the horizontal direction in the output is precisely 0%, so no photons there. However, if the bomb is good, is functional, then a photon is can be absorbed by the detector, and the probability of finding a photon in the horizontal direction is 25%. However, the first beam splitter splits the photons in half, right? So the half of the time the photon goes up, half of the time it goes the horizontal direction, and this is the correct way to discuss it, because we put a bomb, we put a detector here. We don't know either this detector functional or not, but it like measures or not this lower channel with the 100%, with 50% of the probability. So the bomb exploits with the probability of 50%. Okay, so it means that if I put a bomb in this detector and send a photon there to the system, and for example, I detect a photon in the horizontal direction, that automatically means that the bomb is good. The 0.5% of this time, the 50% of this time, the bomb will explode, but another half of the times of the experiment, the bomb will stay unexploded, but I will get the photon in the horizontal direction, which means that this is the indication that the bomb is good and stays unbroken, unexploded. So yeah, so it's very fascinating experiment, fascinating fact, and this was experimentally proven, but of course not with the bomb, but with on other systems, because here the bomb is just for to make this idea more fascinating, more interesting. And of course, instead of the bomb, we can use just a detector that detects photons on a randomly. Okay. All right. So this part was about encoding quantum information into the propagation direction. And now I want to transit to the polarization state encoding. So the polarization state encoding is the way to encode quantum information into the state of polarization. So as you know, the light, it consists of photons, and photons are vectoral particles, and they have the polarization, right? So by polarization we consider the orientation of the plane in which the electric field oscillates. So the simplest state of polarization is the vertical polarization. For example, along axis, in this case, axis y, or axis x, actually. Right, so it's vertical polarization. The electric field oscillates vertically. Magnetic field is orthogonal to the electric field in the propagating field. And in a general case, like for unpolarized light source, for example, like a sun or like a light bulb, such types of sources, they radiate unpolarized light. So the polarization of each photon is randomly selected, and in general you can find any polarization in with any polarization components in the vertical and horizontal directions. Okay, so it can be vertically polarized, horizontally polarized, but also it can be polarized at the 45-degree between these x and y directions, and this angle can be any. Okay, so unpolarized light. And in order to select just one polarization, we can use so-called polarizer. So the polarizer is a system that allows light of one particular orientation to pass through the polarizer. So the polarizer is indicated by this polarization axis. For example, in this picture, it's a vertical polarization, and this vertical polarization orientation of the polarizer allows of vertical polarization of the light to pass through the polarizer. And the other polarizations are blocked. Other polarizations are blocked. If I use the second polarizer and put it in the same state, like polarizer, and the second one is called analyzer, so I put this analyzer also in the vertical direction, it also allows the wave to pass through this second analyzer. However, if I rotate the analyzer by 90 degrees, like shown here, and set it in the horizontal direction, right? So no light will pass through the system. So this second polarizer, it works as a detector, as a measurement setup. It measures the state of a photon in the vertical horizontal state. Okay. So, however, the photon, a single photon in general, can have both polarizations. Both components, the vertical component and horizontal component, and we can consider this vertical and horizontal state as the basis for the qubit. Okay, and we can normalize them, so they are normalized, and obviously they are orthogonal. So if I detect the photon in the vertical state, then I cannot find it in the horizontal state if it was in the vertical state, right? So the states are orthonormal, and I can use them as a qubit. So this picture demonstrates what I basically said. So if, for example, in the input of a first polarizer, you have the superposition of two states of vertical and horizontal states. After the first polarizer, which is set in the vertical direction, it allows only the vertical polarization of a photon to go through, and then using the second polarizer, also set in the vertical direction, it just allows the photon to go through with exactly the same polarization. However, if I set the polarizer in the horizontal direction, like shown here, it completely blocks the photon, so it doesn't propagate through. So it works as a system that can measure the state of a polarization of a photon, either vertical or horizontal. And alternatively, or so I can also take my polarizer and set it in the state 45 degrees. Okay, so it's a mixture of the vertical and horizontal states, and send the vertically polarized photon on this polarizer. And what I would get in the output, I would get the perfect mixture, the superposition of the vertical and horizontal state. Okay, and then I can, for example, put another polarizer in the vertical direction, and again select only the vertically polarized photon. So this polarizer again works as a Hadamard gate, the gate that creates the perfect superposition of, or balanced superposition of, vertical and horizontal states. So how we do so, or how we can create such a optical gates. Okay, so a very useful element here is the crystals with birefringence. Okay, so birefringent crystal is a crystal that has the that affects on the, so better say, the light with different polarization propagates through the birefringent crystal with the slightly different velocity, with slightly different speed. Okay, for example, in this picture, the horizontal state of the polarization propagates. It's called ordinary beam. It propagates with one velocity, but the polarization, the vertical polarization, it propagates with another velocity, and it's called extraordinary beam. Okay, and then of course these two beams coincide in the output, and their interference results, or superposition results in the light state of changed polarization. Okay, so these crystals, these birefringent crystals, allow to change the polarization of the state of light. At the same time, in the single photon picture, we have to consider these two possibilities, this ordinary beam and extraordinary beam, simultaneously. So if we have one photon which is polarized arbitrary in the plane, it can have the vertical polarization, it can have the horizontal polarization, but we must to consider the superposition of them. So the one probability amplitude of the photon propagates through the crystal as an ordinary beam, as the ordinary photon. Another probability amplitude of the photon propagates as the extraordinary photon, and then interfere with itself again, which changes the polarization state of the photon. Okay, so it's also very fascinating and very unusual way to think about the photons and the self-interaction of a photon, not self-interaction, but self-interference of a single photon. But this is the way it is. The single photon interferes with itself. So in any ways, if I consider a plate made of such a birefringent crystal, okay, again, light that passes through this crystal is split into ordinary and extraordinary light beams, each propagating through the crystal with the slightly different velocity. And in the output, these two beams, they acquire some phase delay. And if this phase delay corresponds to the half of the wavelengths, the phase retardation between two phases is equal to lambda over 2, the half of the wavelength. Such a plate is called half wave plate, and this half wave plate allows to conversion of the one vertically polarized light into the inclined polarized light. So like if it was initially polarized in the vertical direction, in the output it will be polarized at the 45 degree to the vertical axis. In other words, it gets the superposition of vertical and horizontal states as indicated here, or in the quantum computing language, this is the plus state. Okay, the superposition. Again, this is another example of a Hadamard gate in the optical quantum computing. If I take the wave plate and make it just smaller, a little bit smaller, so the phase retardation between the ordinary and extraordinary wave gets the value of lambda over 4. Okay, so such a wave plate is known as the quarter wave plate, and the purpose of this wave plate is to add the phase delay of pi, right? So it gets the imaginary unit over here, or it becomes the state plus I in the quantum computing language, or physically, this is the wave which is circularly polarized light. So it's a light with the polarization axis that rotates around the propagation direction of the of light. Okay, so this works as a P gate, phase shift gate, or we name this gate as a S gate, as far as I remember. So it adds this phase equal to imaginary unit between the vertical and horizontal, vertically and horizontally polarized beams. Again, in the language of the single photon, I have to consider these two vertical and horizontal polarizations as two possibilities of one single photon, and I have to consider them simultaneously. And the state, this polarizations, like circular polarization state in the output, is the state of one single photon. Okay. Of course, if I rotate this this crystal, or flip this crystal around, instead of adding plus I would get minus I here. It would be the counterclockwise polarized light in the output. So the wave plate allows to transform the polarization state of light into the state of any type. All right, so all this having said about the polarization state, few words about how we can create the entangled states in the in photonics. So this is much more challenging task, creation the entangled states, because entangled state, as we discussed in our course, requires Bell state, right? It requires application of the Hadamard gate, which is superposition, which is completely, like, very easily achieved by using the wave plate or beam splitter. However, then one needs to apply this control gate, like control X or control Z gate, and this is very difficult to achieve in optics, because this control gate means that the state of another photon must depend on the state of one photon must depend on the state on the other photon in a controlled way. Like if I get the polarization of one photon up, it wouldn't affect the polarization of the second photon, but if I flip the polarization of the first one, it would flip the polarization of the second one. So it's very easy, or very challenging to achieve the operations like this in optics. And the main reason is that the photons in free space don't interact, right? So the photons, as we discussed as we said in the beginning, they don't interact, they don't scatter. If I cross two light beams, they just pass through without interaction. So in order to achieve these two photon operations, we need to bring the nonlinearity to the picture, to the discussion. And the way how we generate entangled states in the lab is to use this effect of spontaneous parametric down conversion. So this effect consists in breaking down one photon into a pair of two photons. Okay, so in the input you have a laser beam which consists of maybe one single photons. They arrive to the crystal, and the crystal is considered to be very strongly nonlinear, with so-called second order nonlinearity. And inside of this crystal, this photon, which is high frequency photon or high energy photon, spontaneously breaks down to two photons. And because of the fundamental properties of nature, for example, energy conservation, momentum conservation, this momentum conservation and energy conservation imply that the photons must be entangled, or at least some of these photons must be entangled. As we can show here, for example, one photon propagates as a cone, right, from the crystal, because this is, well, essentially it's a part of the spherical wave, right? Because every act of the photon breakdown is considered as a point-like source, so it creates the spherical wave. So it's like a cone, and the second photon also propagates as a cone, or probability amplitudes of these photons. They form the cone in space, and the overlap or the cross section of these two cones form the two lines here and here, and these are the directions of the most entangled photons there. So yeah, so people use these photons propagating in these directions here and here as the entangled photons, and this works very well. This type of sources of entangled states is the most most widespread entangled photon sources. Unfortunately, the system not very well scalable, because the scattered photons, they change the frequency, so you cannot put another crystal over here and use this process once again, because this already the photons with the lower frequency, and they don't show this they don't spontaneously break again. But for some applications like quantum communications, quantum cryptography, this type of quantum like entangled states is very well used today. All right, so the state of the art, right? So today's the optical quantum computers, they just started appearing, or development, and this is an example of a very recent system. This system is completely linear, and it operates, it executes, say this way, one particular quantum algorithm, like very specific quantum algorithm, which is linear quantum algorithm. Okay, so it's not really a truly quantum computer, like universal quantum computer in a way that we have, for example, for these IBM quantum computers. But at the same time, we have the nice progress, and people believe that for some types of quantum algorithms, the use of the photonic quantum computer would be more preferable because of the number of advantages, including the speed of light, the weak interaction between the photons, so you can superimpose many states in the single channel, and you can use the light of different frequencies, and so on and so forth. But unfortunately, yes, this disadvantage of realization of 2-qubit and multiple qubit systems, like control qubit, is very challenging, especially if we're talking about the scalable system with multiple qubits, multiple 2-qubit system, 2-qubit gates. All right, and yeah, and of course, optics, especially using this integrated optics, we can put the quantum circuit on a chip. For example, this work published in 2018 demonstrates an example of simple photonic quantum chip with multiple interferometers over here, couplers. So each coupler it corresponds to like a beam splitter, because it allows the light propagates either one direction or another direction, and then if you put together two of these couplers, connect them, it forms an interferometer, and you can control this interferometer. So it's very promising, even without 2-qubit gates. Implementing some simple quantum operations is possible, and of course people actively develop the 2-qubit scalable 2-qubit gates. And this is another picture on the left, is yet another example of more recent quantum circuit with many photons on a programmable nanophotonic chip. And so this work published 2 years ago in journal Nature, and yeah, so it's very nice looking chip, and we can envision a great progress in this area. All right, so here are some conclusions for this part. So first of all, photons have several advantages. Here I color them in blue. So photons offer fast, low error quantum operations, especially single qubit operations. And these operations and qubits themselves, which are photons, they are less prone to environmental disturbances, which make them very preferable, very suitable for quantum computing. Photons can be easily manipulated using standard optical components. For example, the beam splitters, mirrors, wave plates, and maybe lenses, right? So these elements. And photonic systems potentially leverage existing can potentially leverage existing telecommunication infrastructure. For example, the applications of quantum cryptography, they use the optical fiber infrastructure actively for such cryptography systems and quantum cryptography distribution of a key. All right, and at the same time, of course, this approach, as well as any other approach, has a number of disadvantages, and the main one, of course, is that the photons don't interact in the free space, and interact weakly in the even in the nonlinear crystals. So it's very challenging to create a scalable system when you can use a 2-qubit gate and then put another 2-qubit gate on the output and then another 2-qubit gate. So in photonics, unfortunately, it's difficult to achieve. However, there is a great progress in this area, especially in terms of so-called polaritonic systems. So the polaritonic system is a system that consists of a photon and a solid state excitation. For example, a molecule and a photon, or quantum dot and a photon. So it turns out that if one puts such a molecule or a quantum dot, something that can be polarized by the photon, if one puts such an element in a resonator and then excite the resonator with a one photon, then the energy start exchange between the photon state and the state of the molecule or the atom or the quantum dot, depending on the concrete approach, concrete system. And if one increases the coupling between these two subsystems, the polaritonic states appears, which means that the state becomes hybridized. Okay, so it is not anymore a photonic state or the polarization state. It becomes the hybrid state or polariton or exciton polariton. And such exciton polaritons, they are very nonlinear because of the material components there, because of the excitonic state. And this is the very promising way to achieve the 2-qubit operations, 2-qubit gates without the use of these non-scalable nonlinear crystals. All right, so this is basically it for today's lecture. Let me stop the recording and then we can discuss.